This is the fourth part of my lecture on diagnostic accuracy, and I'm going to talk about some further considerations relating to sensitivity and specificity. I'm going to be talking about two things. First of all, verification bias, and secondly, how we extrapolate to other populations. First of all, let's say a bit about verification bias. Verification bias is also sometimes known as post-test referral bias. There is another sort of referral bias that refers to pre-test referrals, so I shall prefer to call this verification bias to avoid confusion. Verification bias occurs when not all of the patients have their true disease status verified by the gold standard test. If that's the case, then we don't know the true answer, so we have to leave them out of our analysis when we calculate sensitivity and specificity. This is a problem if the decision to proceed to the gold standard test is influenced by the result of our test. So if the rate of referral to the gold standard test is different for those with positive and negative outcomes from our test, then the calculated sensitivity and specificity will be wrong, because we've biased the result by influencing those who have the gold standard test as a follow-up. So here's an example of what can go wrong. Here is the data for our beard test, which we've looked at before, and previously we assumed that all patients went on to have the verification by the gold standard test. So out of our 100 patients, we know exactly how many have the disease, how many are men, and how many don't have the disease, how many are women. And we've already seen that we calculated the sensitivity to be 9 out of 50, which is 18%, and the specificity to be 49 out of 50, which is 98%. Those are the true answers. But suppose that although all the patients with a positive result have their disease status verified by the gold standard test, but only half of those with a negative result go on to verification. Then out of our 10 patients with a positive test result, the 10 patients with a beard, we go on to do genetic testing on all 10 of those, so we now know exactly how many are really men and who are really women. But of the 90 with a negative test result, only half go on to have their true status verified by the gold standard test. So we only have 45 in the second row that we can process. So instead of having 41 false negatives and 49 true negatives, we have to halve those to 21 false negatives and 24 true negatives, and that affects the total in the Y present column, which is now only 30, and in the Y absent column, which is now only 25. So when we work out the apparent sensitivity from this biased data, we find that the sensitivity is 9 out of 30, which is 30%, and the sensitivity apparently is 24 out of 25, which is 96%. So you see that we have an incorrect or a biased result for the sensitivity and also slightly for the specificity in this case, by not letting everyone go on to have the gold standard test. Clearly this is the sort of thing that can happen in routine practice, because if your diagnostic test comes up with a normal result, you're less likely to want to go to refer the patient for some verification. Therefore, it is going to possibly lead to this sort of verification bias in working out the sensitivity and specificity. If you want to work out the sensitivity and specificity accurately, you have to make sure that all patients go on to be verified. If they don't, you'll get this sort of bias. But actually, if you know the referral rates of positive and negative results, in this case the referral rate for a positive result was 1, all 10 of our positive results went on to be verified, and the referral rate for a negative result in this case was 0.5, half of our 90 patients went on to be verified. If we know those numbers, we can correct for referral bias by dividing the numbers of positive results by 1, so that is all the numbers in the top row of our apparent table are divided by 1, which means they don't change, and all the numbers in the negative result, that is the second row of our apparent results, are divided by 0.5, which means they're doubled. It puts it back to what it is in the true table on the left. So in that way, if you know the actual referral rates for positive and negative results, you can correct for this verification bias, but you have to realize that it might happen. The other thing I want to talk about is what happens if we have different populations. Because if we know the sensitivity and specificity of the test, and remember that we've already seen that sensitivity and specificity are independent of prevalence, and we know the prevalence of the disease in the population that we are studying, then we can calculate the positive predictive value and the negative predictive value for patients in our population. In other words, we can combine the known sensitivity and specificity of the test with the prevalence of disease in our population to work out the positive and negative predictive values for our population. And the way we do it is using this formula here. It's a bit messy, but it says that the positive predictive value is 1 divided by 1 plus 1 minus prevalence times 1 minus specificity over prevalence times sensitivity. It's a bit of a messy equation. Don't worry too much about the details. We'll see that actually it can be simplified a bit later on. Similarly, for negative predictive value, we have something that's equal to 1 over 1 plus 1 minus sensitivity times prevalence over specificity times prevalence. That result follows from something which is called Bayes' theorem. I'll talk a little bit more about Bayes' theorem later on, and then hopefully this will become a little simpler. For now, all you need to worry about is the fact that these equations simply input prevalence, specificity and sensitivity to tell you what the positive and negative predictive values will be in this population. So as I said, if you know the sensitivity and specificity of the test and you know the prevalence in your population, you can calculate both the positive predictive value and the negative predictive value. Here's an example from the real world. This is actually for a radiopharmaceutical called SPECT. Actually, its proper name is technetium-99 depriotide, an imaging agent which binds to malignant lung tumours, and it was introduced by Amersham in about 2001, and they sold it as SPECT, although now it's marketed by CIS as depriotide. Now, in the SPECT brochure from Amersham Health in 2002, they showed data from 114 patients who'd participated in the original trial of SPECT. So the patients had all had the histology on lung tumours to show whether they were malignant or benign, and they'd undergone imaging with SPECT to see whether they had positive uptake of SPECT or they didn't have uptake of SPECT. And they found they had 85 true positives, 19 true negatives, with 7 false positives and 3 false negatives. So there were a total of 92 patients with positive SPECT, 22 with negative SPECT, 88 who had malignant histology, and 26 who had benign histology out of the total of 114. From that, you can easily work out that the sensitivity is 85 over 88, which is 97%. The specificity is 19 over 26, which is 73%. The positive predictive value is 85 over 92, which is 92%. And the negative predictive value is 19 over 22, which is 86%. And Amersham put all that in their brochure. But they also made this statement. They claimed that a negative SPECT result reliably excludes the presence of malignancy. And that really doesn't seem to be held out by the data. The negative predictive value, that is how useful a negative SPECT result is, the negative predictive value is 86%. That doesn't sound particularly reliable. It means you get it wrong 14% of the time if the result is negative. I wouldn't call that reliably excluding the presence of malignancy. So how do they justify such a statement? Well, when you inquire from the representatives, it turns out that they have extrapolated to a population with a much lower prevalence of malignant disease. Here, in this test population, they had quite a high prevalence. It was actually 77% in the of the patients in their test study who actually had malignancy, and that gives the positive predictive value of 92% and the negative predictive value of 86%, which we've just seen. But if you use Bayes' theorem, you can take other assumed prevalences and put in 70%, 60%, 50%, 40%, 30%, 20% prevalence, and calculate using Bayes' theorem, which I just showed you, the corresponding positive predictive values and negative predictive values. And that's what I've put in the table here. And this is where Amersham's statement comes from. If the prevalence is less than 50%, you see that we get a very good negative predictive value of more than 96%. That's what they're basing their statement on, saying that actually in your population of patients you're not going to have as higher prevalence of malignancy as they had in their trial, and so they are assuming that you are going to get a good negative predictive value simply because you don't have such a high prevalence of malignancy. So they've used Bayes' theorem to estimate what you would get in your population based on what they got in their study. That's what I mean by being able to extrapolate positive and negative predictive values to different populations. But you need to be aware of this, because if the prevalence of disease in your population is not 50% or less, you won't get such a good negative predictive value as Amersham were claiming. And that of course applies to other tests as well. So what we've learned here is that the usefulness of a test depends on the prevalence of disease in the patients being investigated, because positive predictive value and negative predictive value vary with prevalence, and we've seen how that can be applied in the Amersham data case. So a test that is good in one group of patients may not be so good when applied to a different group of patients. So you need to take note of the type of patients studied when reading the published results. They have used a patient population to calculate a positive and negative predictive value. If your patients don't have a similar group of patients with a similar prevalence, then your positive and negative predictive results will be different. And finally, beware of verification bias when calculating sensitivity and specificity in any series that you do yourself, if the result of your test influences who goes on for the gold standard follow-up test. So that concludes part 4 of this lecture.